Question 7. We are given a sphere placed at a certain point on a horizontal surface. Let's call it sphere 1, and the position point it is at is point S, although in the paper it is named differently. It has a charge of plus 3 times 10 to the minus 7 coulombs. And there is a point a certain distance away from the sphere. We will call that point R, and we are told that the electric field at point R is 1.08 times 10 to the 6 newtons per coulomb. First, we are asked what an electric field is. It is a region around a charged object in which another charged object experiences an electrostatic force. Then we must draw the electric field diagram resulting from the charge on the sphere. The sphere at point S is positively charged, so we draw a positive charge. Then we draw field lines radiating outward from the positive charge. The lines should be evenly spaced and not cross each other. Remember, for positive charges, field lines point away, and for negative charges, they point towards the charge. Next, we must prove, using a calculation, that the distance between point R and S is 0.05 meters. We can use the electric field equation for a point charge, which is electric field is equal to Coulomb's constant times by the charge in coulombs divided by the square of the distance from the charge. We are given the value for E, so we can substitute this. We are given the value of Q, and we can get Coulomb's constant from the data sheet. It is 9.0 times 10 to the 9 newtons meters squared per coulomb squared. Solving for R, we get 0.05 meters. We are then told that a sphere is placed at point R. Let's call that sphere sphere 2, and it has a charge of minus 5 times 10 to the negative 7 coulombs. And another sphere is placed to the right of the initial sphere, and its charge is minus 4 times 10 to the negative 7 coulombs. And the distance between sphere 1 and the new sphere, which is sphere 3, is 0.04 meters. We are told that there is a net force acting on the middle sphere. It is 0.0427 newtons. We don't know yet in which direction this net force is acting. But since all the spheres are in a straight line, and since the outer two are negatively charged while the one in the middle is positively charged, we can deduce that the electrostatic forces acting on the middle sphere act in opposite directions. The outer two spheres both attract the middle sphere. We are then asked if there is friction on the surface or not, and we need to deduce this by calculation. Now, if there was no friction, then the difference in these forces will exactly equal the net force given to us. So let's calculate the two electrostatic forces acting on the middle sphere and then subtract them to see if the difference is equal to the net force given to us. The force between two charged spheres is equal to kq1 q2 over r squared. We can use this equation to find the two electrostatic forces acting on the middle sphere. We have Coulomb's constant for both calculations. Then in the first calculation, the product of the two charges for spheres 1 and 2 over the distance between them squared. And in the second calculation, we have the product of the charges on spheres 1 and 3 over the distance between them squared. Then solving, we get 0.54 newtons pulling sphere 1 to the left and 0.68 newtons pulling sphere 1 to the right. The difference in these two forces is 0.14 newtons to the right. But remember, we are told that the net force acting on the middle sphere is only 0.0427 newtons. This is less than the net electrostatic force. So yes, there must be friction. And no, the surface is not frictionless. Lastly, we are told that sphere 2 is allowed to touch sphere 1 and then is moved back to position R. And we need to say what happens to the magnitude of the forces exerted on sphere 2 by the first sphere. When spheres 1 and 2 touch, charge is transferred between them. The charge is redistributed, and they share the overall charge equally. So we can add the two charges and divide by 2 to give the new charge on each sphere after touching. They will both have the same charge after touching, that is, -1 times 10 to the -7 coulombs. Initially, sphere 1 and 2 attracted each other as they had opposite charges, but after touching and sharing the charge equally, they both became negatively charged, and so now they repel each other. If we now find the electrostatic force between these two charges, we get 0.036 newtons. This force is smaller than the initial force between them. So we can say that after touching, the force between the two spheres decreases.